So it's great to be back. I was telling Farah that last time I was here was probably years ago, but it's always good to be back in this room and presenting. And I like that we have a little bit of a smaller crowd because now it might give me the opportunity to show you guys some of the other things that are slightly more exclusive, but we'll see how things go and whether we have time or not. So today I'm going to be talking a lot about parking, pricing, detection technologies, and so on. As a little bit of background, parking does contribute significantly to GHG emissions in terms of monetary values and CO2s that are generated from them. Emissions, for example, in terms of parking infrastructure is estimated to cost somewhere between 4 to 20 billion annually in the US, or between 6 to 23 per space per year. And a proportion of that is related to the vehicles cruising. So you know that there's lots and lots of other challenges with parking. For example, lack of parking availability. Naturally, a lot of times if you're parking in dense downtown cores, it might be difficult for you to find a parking space, or illegal parking causes a lot of issues with respect to how it affects other modes of transportation, the safety concerns that it creates, and so on. So parking management strategies are put in place by parking authorities to try to alleviate some of these challenges. In Toronto, the main authority is who? Does anybody know? The main authority that controls
Green P.
Green P, which is the company?
Toronto Parking Authority.
Toronto Parking Authority, exactly.
It's a city agency.
It's a city agency that takes control of the parking management strategies. And you can think of policies in terms of three main aspects. So pricing is in place for them to balance supply and demand. Information systems to help drivers find vacant parking spaces faster. And emerging technologies, I'll talk about some of these emerging technologies that are happening in the parking world. And essentially they're put in place to improve the capacity utilization that we have. So if you think about the concept of ITS, the concept was originated because we had saturated capacity in terms of how we could expand infrastructure, and that was a few decades ago. People started to think, okay, we cannot expand our road network anymore. Let's try to find newer ways that we can utilize it in more efficient ways. And parking is kind of at that stage right now where we know we cannot increase parking supply. In fact, as we were talking earlier on, you might want to reduce your parking supply because when you have parking in places that are very high in real estate cost, then it doesn't make sense to have a parking space cost you very large amounts of money. So whatever we can do to reduce or improve our capacity utilization goes into emerging technologies. I'll start talking about each of these one by one, starting off with pricing policies. So some of the main pricing policies that cities are interested in and they're applying are hourly pricing, which is typically what TPA is doing. You pay per hour that you park, right? And they modify this in certain ways in the sense that sometimes there is a maximum allowable parking time that you have. Like I think the common limit is 3 hours. So you can park for 3 hours, there's a pit, there's an hourly rate, and then you have to move your car or do something. There's time of day pricing that's implemented in Toronto as well, where you pay a rate for off-peak and you pay another rate for the peak, so that they're trying to create some sort of balance with the supply and demand. And the two other ones that Toronto is considering are progressive pricing and dynamic pricing. Dynamic pricing has been around for a little while, and I'll talk about it. I'll explain how it started and what stage we're at right now. Progressive pricing is more new. And the way they work in progressive pricing is you pay a certain rate for up to some threshold, and then that rate increases. So for example, in that figure, you're paying $4 per hour for the first 4 hours, and then any additional hour that you park, you have to pay 8 hours. Why do you think they do that? Why have this increase in the rates? Why? What's the purpose?
Limit the past night period.
Exactly, to shorten long overstays, right? Instead of putting a 3-hour limit, because a 3-hour limit is ridiculous, right? What if you need to stay a little bit longer? It's happened to me before, and I actually got a ticket when I was down here visiting the SFC meeting, I got a ticket because I stayed more than 3 hours, slightly longer. So if it's a progressive pricing strategy, you're like, okay, I need to stay for another hour anyways, so I just rather pay the additional rate rather than having this cutoff. So that's something that's being considered. So in a sense, you can think about it as it's parking duration responsive in the sense that it looks at how long you're parking and your rate increases. And dynamic pricing is essentially adjusting the prices according to the demands that you observe. So if in some locations you have higher demand, you want to increase your price. In locations you have lower demand, you want to decrease your price so that you can create a balance between the vehicles, have some transfer of flow of the vehicles between these parking groups. Yes.
Is that what they did in San Francisco?
Yes, yes.
Where they like price it?
Park. Yeah,
Yeah.
we're gonna get to that. Essex Park is the first example of it. And so in that sense, you can think of this as occupancy responsive because, you know, when your occupancy is low, you do something, target occupancy, you're happy, high occupancy, you know, you adjust your prices accordingly. So I'm going to talk about some of these. I'll start off with hourly pricing, which is the basic one implemented almost everywhere. In terms of econometric modeling, if you think about it, what the parameter, the variable that would be of interest is how long people are parking, and how can I adjust the parking rate so that I can manipulate people's parking durations, right? Because if it costs $5 rather than $3, then you're likely to shorten your trips, right? Imagine you're out for a shopping trip. If it's cheaper for you, you will stay longer. If it's more expensive, you will try to shorten your trip. So in terms of econometric modeling, you can think of this as a simple supply-demand curve where you have parking duration on your x-axis, on your y-axis you have the marginal utility. So this essentially shows you how much utility somebody is getting per hour of parking, and naturally this is a decreasing function because the longer you stay, the lower utility you get per hour. Whenever you're shopping, that first hour of shopping is more valuable for you than the second hour of shopping and the third hour of shopping. So it's the marginal utility function, and the price is P dollars per hour. The point where they cross each other can be considered the equilibrium point. And naturally, when we have data, you have really good data around this point because you know, okay, how many people are parking, you know the parking price, and you have good information about this point. But if you consider like a linear marginal utility function, you need another point to come up with this utility function. So sometimes people consider like a maximum dwell time, like they say people are not going to park more than 5 hours or whatever. So they can get 2 points of this and they can characterize the marginal utility function, the equilibrium point, and then naturally they can see what happens when they play around with this P. If they reduce the P, what's going to happen to the parking duration? It's going to increase because your equilibrium point is going to be further down, and so on. So by manipulating the price rate, you would be able to adjust average dwell time of people. So that's the simple case. Moving into the two more complicated cases of progressive pricing and dynamic pricing, the idea is like this, as I said, is you have a pricing structure where people pay P1 for the first Q hours and they pay P2 for the remainder hours. And this kind of stepwise pricing structure is already being implemented in a lot of places, both in the public sector and in the private sector. So if you look at this list that we have, this shows you some of the locations where progressive pricing is being implemented. And you can see that it also shows you the costs of the steps. So in Aspen, Colorado, the first hour is $3, second hour is $7.5, third hour is $13.5, and fourth hour is $21. And you can look at how some of these steps are going up and down, but naturally it's a progressively increasing price rate that they implement in order to avoid long overstays of parking. Now, if you think about this kind of a pricing structure and you reconsider the marginal utility functions in blue and red, and let's just say that we have two types of users. We have a high demand, high value user, and we have a low value user, represented by these two different colors. And so we classified users into two main groups, high value and low value in terms of marginal utility. You could have three different cases in terms of how these marginal utilities cross the pricing structure, right? The pricing step. Which of these do you think is trivial and should not be considered? Out of A, B, and C. Give it a thought, and then I'll ask you Which of the three you think is trivial and should not be considered? How many people say A? How many people B? How many people C? Why C? Anyone want to share? You want to share with us why C?
They even, the utility even did not go to this stage too.
Exactly, exactly. It's trivial because if you price it like that, then this is essentially ineffective. This is hourly pricing. It's not progressive pricing, right? Because both groups are essentially just paying P1. So it's as if you set your queue to a really, really large value, like 10 hours. Who's going to park more than 10 hours, like 20 hours? So that case becomes trivial, and then we have two cases that are more meaningful. And in these two cases, they also have some intuition behind them, because if you look at this one, this is sort of a market segmentization strategy where you're pushing the first group to pay P1 and the second group to pay P1 for the first few hours and P2 for the remainder. And if you think about it that way, you can characterize the utility of each group, where you have the marginal utility UI, parking from 0 to D. Can you see my, okay, good. And this is the marginal utility function minus the cost of parking, which is related to D. So the cost of parking, if you're parking less than Q hours, is P1D. If you're parking more than Q hours, is P1Q, because you're paying for the first Q, and the remainder of that, which would be P2 times D minus Q. And this kind of characterization allows us to come up with the equilibrium dwell times, which are here. And so for each group, we can assess where they would be parking, how long they would be parking. So without going, I don't want to go too much into mathematical details today, because I always think it's better for you to read papers and go through the details, understand everything. But I want to talk more about insights and outcomes and what's the final result of some of these analyses. So when we looked at here at profit and social welfare maximization, because these two objective functions are typically what a lot of public agencies are interested in, especially like parking agencies, because parking is a source of revenue for the city, and so they care about how much money they're making. They're not just incredibly nice people that don't care at all about money. They care about money. So profit is important because parking is a main source of revenue for the city, and social welfare is the other important factor. Social welfare is more of the social well-being of that policy and how well people are, getting service from that particular policy. So what we found out is that the optimal revenue maximizing policy in progressive pricing, the low value pays the base price and the high value pays the augmented price. So if you're maximizing profit, this is the kind of strategy you want to implement, because like I said, this is much better at market segmentization than other ones. It creates more of a distinction between the two groups and how much each of them would have to pay. Whereas if you're maximizing social welfare, then, and in fact what we found out is that the Q and the prices are all irrelevant. If you just care about social welfare, you just want to set your P1 to your P2, and then Q is not even important. And there's a logic behind that, which requires a little bit of technical discussion. But the logic behind it is that when you move this Q around, what happens is the additional revenue because social welfare is the revenue for the city plus the plus the consumer surplus in economic terms. And if when you move this around, the trade-off between them is 1-to-1. And so for social welfare, it's not that great. For profit, it's a good way of segmentizing their demand. Some results out of this analysis from the downtown core of the city of Toronto. So we received data from GreenP, and we analyzed this data to create a simulation and assess these kinds of different policies and see how they're behaving. So this was the study area that we were looking at in a joint project with the Toronto Parking Authority. And this is some of the high-level outcomes of the TPA data. So there on top, you're looking at the number of transactions in different days of October in 2019. And the red bars are the weekends. So you can see that in one area, the weekends have a drop in demand, whereas in the other area, the weekends have an increase in demand. So behaviorally, they're very different. in terms of how they're acting. And we also give these distributions of parking duration, how long people stay there at these two different spaces. And what this allows us to do is it allows us to create a simulation model where we take this data and we use a simulations SDK to tell people, okay, where are you parking, how long are you parking, and assess the impact of different policies. So this is a simulation of VISM in our study area, where we use the software's SDK to incorporate the parking behavior. So you can see some of the vehicles are already parked here. So through the SDK, we tell a vehicle where to park, and through the policy structure, we tell them how long to park. So if it's like progressive pricing, they're pushed to pick a specific dwell time depending on that econometric analysis that we did. So let's just wait. So this is an actual case where a vehicle parks, decides to park in this parking lot, finds an empty spot. Oh, this one is full, comes to the next one, finds an empty spot and parks there. And because we have access to the entire simulation, we can control everything, implement our policies, and do our analysis. Some of the results out of this simulation are when you compare hourly pricing with progressive pricing and looking at the different parking locations. So these are 54 different parking locations which are sequenced in terms of their parking occupancy percentage. So the blue line is the hourly price and the red line is the progressive price. So what you can see here is that the parking occupancies are slightly lower in the progressive pricing compared to hourly pricing. They're slightly lower. In some cases they go up. And in parking requests decline, so when a vehicle goes to the chosen parking lot and they don't find a space there, they're considered to be declined. And you'll see that the decline rate is also slightly lower in progressive pricing compared to hourly pricing. And then also when you look at the occupancy levels versus the decline rate, naturally this type of curve should make a lot of sense because the higher your occupancy, the higher the chance that you might get rejected when you go to that space, right? There may not be enough spaces for you. So you'll see that this shows you that kind of trend when your occupancy is relatively low, then chances of you getting declined is 0, but it goes up after some threshold. And you can also look at the colors, which compares hourly pricing, time of day pricing, and progressive pricing. It shows slightly better results. But summarizing these results in terms of different KPIs, so we have here the measures, parking occupancy at high demand locations, at low demand locations, and cruising for parking, total network travel time. What we see is that in high demand locations, it's able to improve parking occupancy by about 5%. In low demand places, it's not that effective because already there's already enough spaces, so why implement this more complicated policy? And cruising for parking, it reduces by about 10%. But the important thing is we shouldn't always say this is great, let's do it, it's the best policy, because that's not always the case. We have to tell the full picture. And the full picture is that your total network travel time does not change drastically, which is something that a lot of parking enthusiasts claim. They say, oh, 30% of vehicles on streets are cruising for parking. And some people are challenging some of these statistics. So from our simulations, we show that the actual increase or decrease in the parking total network travel time is not that significant. Moving into dynamic parking pricing now, if any of you are not familiar with it, the idea is how you can adjust your prices based on your demand so you have a better balance of your parking occupancies in the system. So let's look at a base case where you have regular hourly pricing. Let's say you have street 1 and street 2. In street 1, which is like near leisure places, your occupancy is, let's say, 100%, pretty much full occupancy. Let's say your price is $3. Street 2, same price, but your occupancy is 40. The idea of dynamic pricing is to adjust these prices so that instead of having 3 and 3, you get like 4 and 2, and maybe this allows you to transfer some of the demand from this parking lot to the other parking lot. So that instead of 140, you can go with 80 and 60. It's a way of rebalancing the demand that you have in your system so that you would be able to keep some empty places everywhere for people that are looking for a space. That's the idea behind it. And there is lots of best practices of this. The first one is you said San Francisco as a park, implemented in 2011. That was pretty much the very, very first example of dynamic pricing. And what they did is they used these in-ground sensors that I'll talk about more. There's just these magnetic pucks that they put in the ground that creates this electromagnetic field above it, and if the vehicle parks on top of it, it knows there's a vehicle here. And they operated for 3 months. Their target occupancy was 60 to 80%, so they wanted like all the blocks of the street to have an occupancy of somewhere between 60 to 80%. And they tried it out at different locations and different times. These are some of the other examples. Los Angeles, LA Express Park in 2012. They also used ground sensors, worked for 3 to 6 months for 70 to 90% occupancy. When you look at the other kinds of sensors and data called occupancy detection methods, so a lot of them had in-ground sensors. Some of them had, just survey methods, which are not that ideal because like how frequently can you collect a survey? A sensor is there and collecting data all the time, but like how frequently can you go out there and manually collect the survey? And some of them a mix of these strategies. And so that's one very important aspect of dynamic pricing, how you're actually collecting your occupancy data. But the other important aspect, the other two are how frequently are you changing the prices? Some people are under the wrong impression that when you say dynamic pricing, you're thinking about like minute by minute changes in the price. That's not the case. Why would you not want to do that? Why would you not want to? Isn't that great? Why not change your prices?
For the end user.
Sorry?
It's confusing for the
Confusing for the end user.
What is the frequency of relaying information to the
Exactly.
end user?
It's confusing for the end user, yes.
Also with parking, someone like the other places like they use dynamic tolls, but with a dynamic toll you can just decide, oh, I'm not going to take a toll route. But with parking, you need parking once you've decided to drive to your destination.
Yeah.
So when they show there and it turns out, oh, parking is $100 an hour is an extreme case.
Yes.
They can't actually do anything about it. They've got to pay $100 or what? Like, where else do they park? You know, they park in the middle of the road. Okay, they're going to get the car towed away pretty quickly.
Yeah.
You know, they park in the middle of the sidewalk.
Yeah. Psychologically, it's also, I agree, it's a bigger concern. For me at least, you know, when I'm ever considering driving, I'm like 407, 401. Okay, I'll pick it's much of a more flexibility in my decision making, but psychologically it does create this, it has this burden on you, and it can create confusion. You know, what if I thought this was $3? You know, and you'd be surprised how much backlash you get from parking. You know, if you increase 50 cents, people are going to have backlash. Let alone in changing them drastically enough for people to change behavior. So look at these refresh rates. That's the wrong impression that people have. These refresh rates, the smallest one is 3 months. So that's
2 months actually. Boston.
2 months. Sorry, 2 months. Yes, 2 to 3 months. And I think there's actually a 1 month one too. I think 1 month is the smallest we could find, but it's much longer than an hour or a day, right? So they look at total months. It's essentially not dynamic pricing because it gives the wrong impression. It's just price adjustments given the
It's
lots
just
of regular.
It's like increasing fares or something every now and then.
Exactly. But you do want to have some system in place because if you don't have this, then you end up having the same prices for decades, which does happen in a lot of cities. And target occupancies as well. You can see that some cities are going for different occupancy levels in the sense that they try to keep it around that percentage. So more on these case studies, San Francisco claimed, I think San Francisco is exaggerating a little bit when you compare to other ones, but because they were the first people to do it too, maybe nobody really kept them up to their promise. So they say it doesn't increase 16%, which is realistic. Cruising was down for 50%. This is something I question because how do you measure that? How do you know the pre-policy, the after policy? It's a little And time to find the space reduced by 43%. Park DC and LA Express are a little bit more realistic. Average time to find a parking space reduced 2 to 3 minutes. Time spent circling decreased 7 to 15. And in LA Express, congestion decreased by 10% and 76% of the drivers saw benefit. So those are a little bit more realistic. Yes?
Just a second, is the SF Park thing still underway? Because it said 2011 to 2013.
So it's underway, but no longer with sensors. With the magnetic sensors that they have, it's no longer operated under that magnetic sensors.
So do they do manual surveys? Like how do they choose?
I think so. I think they do manual surveys now. But we'll talk about some of the methods, and you'll see the reason. This is actually one of the reasons where they were not sustainable in using the method that they have, the technology, and it's their occupancy detection method. So if you think about occupancy detection methods, these two are the most common ones, using sensors or the magnetic pucks that I told you about, and what's it called? I think that's Pebble is Google's device. Google Sidewalks created Pebble, but even their technology is not, at least to me, wasn't readily accessible. I'm not sure where they stand with it. The problem with these kinds of magnetic sensors is that advantages are, okay, they're efficient, they're great. You know, you can put this sensor every time there's a car on them, so that's, what else can you want? It's fantastic. Provides real-time data too. So what's the problem? The problem is high maintenance and installation costs, because you're actually installing these in pavement, and cities, they always want to stay away from adding infrastructure unless like the benefits are evident to them and they're huge. So lots of people stay away from this, and I personally don't think anybody has championed it in practice. Cameras, installation can be easy, it has real-time data, it's expensive and needs mounting. In fact, we've looked into installing cameras with the support of the City of Toronto, and we spent like a couple of months, I think some of you know, to do it, and we weren't able to do it because of what's called pole politics. Because every time you want to mount a camera on a pole, somebody owns that pole. It's hydro, it's somebody, and it's like they have ownership over that pole, and you can't install it anywhere that you like. And so with even though this was a City of Toronto project, after months we were not able to find one location where you could put a camera. Think about that. So there's no way almost that we can scale this. It's almost impossible to scale pole mounting cameras. Now the new one, which is what we're looking at, and it seems to be something that cities are going into recently, is transaction data. There's no installation cost, so transaction data is a green P data. If you have like real-time green P data, can you use that data to make some inferences about...
So like people buy in the app or something?
Exactly. When people buy, can you use that information to infer like what the occupancy levels would be? And but it does have some challenges too that we'll talk about in a second. What do you guys think that the challenge would be with transaction data? Yeah.
The people who don't pay.
Exactly.
You get the parking.
Exactly.
Now, could you maybe double check it, like when you got the parking enforcement officers, or what my grandmother calls green hornets. When you got the hornets come by, could you have them like double check it? Because they would like say, like you could have the parking enforcement officer go through and say, like, I counted 5 cars when I was checking Bloor Street.
Good.
And then you could like compare that, because if you said 5 cars, but you've only got 3 cars according to the transaction data, you know, okay, there's 2 cars that are illegal, they just got tickets from the parking warden, that will go by the 5 number.
You're thinking ahead, exactly. That's the way to do it. It doesn't necessarily need to be enforcement officers. You need to have some form of way that would allow you to check.
It doesn't have to be every time though, but
Exactly.
I'm just saying parking enforcement, because they're going to probably be coming by there once or twice a day anyways.
Yes.
So they might as well you've got the data already from them, because you know, oh, they find this car based on the license plate, and they find that car. You can infer, okay, we just have to add them to the tally.
Exactly. So high level, it's cross-validation. Regardless of what your strategy is, you need some cross-validation so that when you go from data to occupancy predictions, you need to have some cross-validation to improve the accuracy of your models. So people that don't pay, or people that overstay or understay their parking payment are also have to be considered. If you're understaying, it means, okay, you paid more than you stayed, so you're creating some sort of error in the system. And if you're overstaying, then you paid less than you stayed. So in a way, you're illegal parking for that remainder of what you didn't pay for. So the way this data looks like, the transaction data from GreenP that we have access to is, like the location ID. So the way they operate, if any of you have parked downtown or are familiar with GreenP, is that a bunch of parking spaces are given one ID, right? So if you're parking like on one block side, there's an ID written somewhere. So when you go on the app, you type in that ID, and all of those spaces are considered together. So the data that we also have, we don't know exactly out of these 10 spaces which one is occupied, but we know out of 10, 5 have paid within this much. So you have the IDs, you have the on-street, and you also know when somebody paid and how much they paid. That's the information that you have. You know when somebody, the timestamp when they pay, and you also know the dollar value of how much they paid. So if you know the dollar value and you know the rates, let's say they pay $10 and the rate of that space is like $2 per hour, so you can approximate, they approximately pay for $5, given the, give or take, the overstays and the understays. So the first natural thing we can do with this data is, by the way, not a lot of research is on this, but I found out some parking consultancies have already adopted some form of this approach, which is a simple approach, but it's just not widely applied, which is surprising to me because the data is pretty much available everywhere. Almost every city has parking transaction data, but they rarely take advantage of the value it can provide. So these are the occupancy profiles. So if we know exactly when somebody paid and how much they paid, we can come up with an occupancy profile that looks like this for 3 different days and at different accuracy levels of 1 minute, 15 minutes, and 30 minutes. So you can see that the red line, it's a little unclear, so I'll explain what the X and Y axis are. On the X axis you have time of day. On the y-axis, you have occupancy, and the red line is the capacity, how many spaces are available. Naturally, you don't see the blue lines crossing the red line because we can't go over capacity, although there is some outliers in the data, but naturally, in regular cases, you shouldn't have the blue lines crossing the red line. And depending on how much accuracy you're interested in, if you're working with 1 minute, it's too detailed data, you may experience overfitting, and when it's really 1 hour, 2 hours, you lose a lot of detail. So we found out that 30-minute profiles are probably the most logical that we want to work with. And as you guys mentioned, the main challenge, the first big challenge of this is that we don't have the non-payers, we only have the payers. So in fact, if you want to correct this, maybe the correct one looks like that, or those, or yellow ones are the non-payers that have to be considered. But in order to do that, as you mentioned, you need to have some form of cross-validation. So maybe we can have a temporary camera. We're not permanently installing a camera. Permanent installation is almost impossible, but temporary installation is possible, right? You can have somebody go there with a camera or just on a simple pole and record for a day. That's feasible. So you can cross-validate and find out, okay, from the information that you have, I infer that there's going to be these non-payers at those times, and this allows me to create some more accuracy in the predictions. Looking more at the different times of day, so by default these do start to provide some details. So in this particular location, you see that the weekdays are less congested than the weekends. On the weekends, you can see that the occupancy profiles are getting pretty close to the demand. And we can do further analysis on this. So these red lines these red lines, if you see on all 3 days are the same. These are the average occupancy levels for that location across the whole month, right? So if you get the averages across the whole month, then what this allows you to do is you can compare particular days or instances with the average. So you see here, for example, that on Mondays, occupancy was larger than the average in the mornings, in the afternoons, and towards the end of the night. whereas in some cases, occupancy on Wednesdays, it's lower than the average and so on. So by default, you can comparing the averages of the whole month with just specific days, you may be able to create these kinds of analyses and find out, what's happening on particular days and what you can do to improve the system. Next analysis from the data is the average, is how much people pay versus the arrival count, how much they paid versus occupancy for 3 different times of the day for 10 locations. So you can see that these blue ones are the morning. You can see in the morning people are paying more money and staying for longer hours. These are probably maybe commuters. And then you can see towards the evening people are paying less money and staying for shorter periods of time. And that also shows itself in the occupancy levels. So you can do this kind of time of day analysis and see what's happening. Or you can also do pricing analysis. So again, we have the rates at the bottom for 3 different times of the day. And you can see that in the mornings, when you go from $2, $3, $4, and $5, the changes are relatively mellow because probably when you have inelastic demand in the sense that people need to go there, regardless of how much you charge, you don't see a lot of differences. But when you see afternoon and evening, where trips are more for leisure and those kinds of patterns, you see that the prices do make an impact. When you go from 2 in terms of occupancy, when you increase the price here, the occupancy has actually gone up, which is a little counterintuitive, right? Because you would want the occupancies to go down, but occupancies have actually gone up. It means that people are so inelastic to prices in some of these cases. You're charging them more money and they're staying for longer anyways. So it goes on to to raise some questions of how efficient are these prices implemented, right? How does that make any sense to us? So those are some of the things we're investigating. But our methodology for investigation is we can't be comparing all of the parking spaces together all the time. You have to see how close they are to each other, right? If 2 parking spaces are very far from each other, it doesn't make sense to compare between them and say, okay, I'm going to increase the price there, decrease the price here. They're too far from each other. They're not within people's same choice sets, right? They're in different choice sets. So you have to look at making adjustments in parking spaces that are within the same choice set. And the way you do that is, the way we do it is we look at distances. So let's say you have 2 parking groups that are within a relatively short walking distance of each other. And those are the kinds of analysis we do. We focus in on close proximity parking locations. And we get some interesting cases. So in one case, we see that both rates are, one rate is $4, one rate is $5, but you see that the occupancies are relatively close to each other. Whereas in this other case, you see that similar kind of situation, $4 and $5, but you see that the occupancies are drastically different from each other. So this kind of analysis allows us to zone in a little bit on cases where these price adjustments would make sense for us. And so this creates the approach for kind of a clustering method where we look at clusters of parking, not all of the parking lots together. So if we're making adjustments, we make adjustments in this cluster, in this cluster. We're not going to change this price with another price, assuming that people are going to transfer from here to there because of dynamic pricing. So it's a clustering, network-based method that we use to understand where we need to make changes and how we make those changes. This is our parking proximity network. So depending on what the walking distance is, 100 meters, 150, 200 meters, 300. So you can see that when the walking distance is short, your network is quite disaggregated, but as you increase that threshold, you see that your network becomes more like a connected network. And this allows us to further analysis in terms of the network science of these parking lots. And the network science of this is some of the metrics that are highly important. If any of you are familiar with these, are the node degree, the eigenvector centrality, betweenness centrality, and closeness centrality. So the node degree, which is this, is essentially how many links are connected to each node. How many links are connected to each node, and this is a distribution of it. You have node degree and you have distribution. Naturally, as you increase the walking distance, this thing pushes itself forward. And you'll see, for example, that when your node degree, when your distance is about 100 meters, your node degree is relatively around 1, meaning that only 2 parking spaces are within close proximity. But when your distance is like 300, then your node degree is around 6 or 7. So every parking space has 6 or 7 accessible spaces around it. Eigenvector centrality, which is interesting, is the measure of the influence of a node in a network. So you assign relative scores to the different nodes of the network, and this tells you what these, so each node scores depends on itself and the score of its nearby nodes. And so this is interesting because it shows you that as you increase that walking threshold, the eigenvector centrality is not changing that much. So regardless of what that walking measure is, the importance of the nodes remains the same, which is very important here. So it shows that it's relatively independent of that walking distance. And then you have betweenness centrality and closeness centrality. Betweenness is basically for a pair of nodes in your graph, whether a shortest path crosses that node from that node to any other node. So it shows you how central a node is to your system, and closeness centrality is something very similar as well. So some of the results of this modeling that we've done, I'm going to show you in online now. So this is we decided, one of the things that my lab is heavily moving towards is developing dashboards and tools. We see a lot of value in it because, oftentimes when you have partners, and you do the most fantastic types of modeling and everything, that's great, but it's really difficult to convey that information to your partners and tell them, I built like this network science model, there's graph neural net, they don't understand that so well. So you need to be able to visualize it and show them the final outcomes. So this is an ArcGIS dashboard that we have, and it shows you, how many people here have experience in ArcGIS? Good, how many people have an ArcGIS dashboard building? Good, I highly recommend it. I think it's relatively easy to pick up and gives a lot of value. The benefit of a dashboard is that you can log into it from just a regular website. You don't need to have an expert in ArcGIS to access your model and play around with it. So you just build a dashboard, which is essentially a data visualizer, is essentially what it is. And so this is the outcome. So for example, you can pick your filters here, whatever you like. These are basically the percent hours, the percent available hours purchased. So you can look at the number of spaces, revenue per space, total revenue, and parking area prices. So this one's like $5, $4, and so on. And you get the percentage of how many are $5, how many are $3, how many are $4. On the left, you get occupancies, total occupancy, time of day occupancy in the morning, evening, and afternoon. And at the bottom here, you have the parking ID and the occupancy percentage. And here we do a comparison between dynamic pricing and hourly pricing in terms of the price profile. So you can see there's more variations in dynamic pricing. Some of these prices have gone up, some have gone down. At the bottom, we have some revenue measures for the locations. How much revenue is each location generating? How much hours is being bought per location? And what's the revenue per space? I'm getting close to time. So where I want to close is these types of dashboards. The reason you call them a dashboard is because it's just a data visualizer. It does have some interesting intuition in the sense, for example, let's say I want to focus in on these spaces. Let's say this is an area that I'm interested in, and I can come here and I can pick some of these locations, for example. And my information will be filtered for specifically what I selected, and I can do further analysis. I can do cross comparison between those locations. So right now I picked 1, 2, 3, 4, 5, 6 locations. I can see, and they're close to each other. I can see some of them are at higher occupancy, some of them are at lower occupancy. I can look at the differences in dynamic and hourly pricing rates, the revenue, and so on. So in that sense, it's a little interactive. But it's just interactive in the sense of how you filter information, right? So my last point is where a lot of my research is going, and what excites me a lot is to build tools that are truly interactive, that would allow our partners to interact with them, give it new information, visualize new things, and so on. So we're building one for parking right now, but I'm going to show you two other examples that are closer to completion, and I'll close there. So this is one tool that we're developing for emergency response management. This is where fire stations are. So these are this is for the city of Vaughan, and my screen is broken. So this is for the city of Vaughan, and you can click on the fire station, and it shows you like 2, 4, and 6 minute contours, and you can move it around. So this is interactive in the sense that when fire chiefs want to see what happens if they move a station around, they will be able to do that. And they can change and manipulate the fire region district as well. At the bottom, they get all these kinds of analyses. So let's say this is showing the entire system. They can see if they go on local properties and they change a fire station, they can see that as they move this fire station, they can see how many of them fall within 2-minute, 4-minute, and 6-minute boundaries. And then they have modules on the left. They can do like different kinds of filtering of the data. They can pick the call category that they have, and all these kinds of things. They have different modules here as well. Let's say somebody wants to add a new station in this area where they don't already have one. Let's say they want to add one in Nashville Road. So they just write Nashville and Vaughan. They select it, and then they can add a station. Once they add a station, they can start to manipulate its boundaries and so on. So here they can manipulate these district boundaries and make corrections. So the good thing about this is that it's not as complicated as ArcGIS, because a lot of your partners in the future or your employees, whoever, are going to want super simple things to do. This doesn't require ArcGIS training. It's easy to do. And there's other things they can do. They can, for example, animate how their data is propagated throughout the course of a day. So here they can animate their demand and so on. So I think this is what you can call a tool, because it's highly interactive. You can add data to it, you can revise data, you can modify data, you can generate all kinds of different analytics, you can add different kinds of modules to it, optimization, animation, prediction, and so on. And these kinds of platforms, in my opinion, are perfect for creating that bridge between your research and something that actually goes into practice, something that is often missing in academia, because a lot of our work just ends up going into papers. And if you could push for something like this to make it more realistic, I think it goes a long way. Thanks, guys.